Greetings and welcome back to the fourth video of the series in Trend Lines and Regression Analysis. In this particular video, we are going to look at multiple linear regression. A linear regression model with more than one independent variable is called a multiple linear regression model. Simple linear regression model is just a special case of multiple linear regression. A multiple linear regression model has the form y equals to beta naught plus beta 1x1 plus beta 2x2 plus ... beta kxk plus epsilon. Okay, where y is your dependent variable, x1, x2, x3 are independent variables, okay, or explanatory variables. Beta 1, beta 2, beta k are regression coefficients for each of these independent variables, and epsilon is the error term. We estimate the regression coefficients called partial regression coefficients B0, B1, B2. Then we will use the model. Okay, y hat equals to BO plus B1x1 plus B2x2 ... BK xk. Okay, the partial regression coefficient represent the expected change in the dependent variable when the associated independent variable is increased by 1 unit, while the values of all other independent variables are held constant. Okay, we can use the ANOVA test, okay, on multiple regression as well. Okay, however, in the multiple regression, ANOVA test is used to test the significance of the entire model. Okay, that is, it computes the F statistic for testing the hypothesis, where the null hypothesis, okay, beta 1 equals to beta 2 equals to beta 3 all the way to beta k, which is equals to 0. Okay, and the alternate hypothesis is that at least one of these beta value is not equals to 0. So what this actually does is that the null hypothesis states that no linear relationship exists between the dependent and any one of the independent variables, whereas the alternative hypothesis states that the dependent variable has a linear relationship with at least one of the independent variable. If the null hypothesis is rejected, we cannot conclude that a relationship exists with every independent variable individually. The multiple linear regression output also provides information to test hypotheses about each of the individual regression coefficients. If we reject the null hypothesis that the slope associated with the independent variable I equals to 0, then the independent variable I is significant and improves the ability of the model to better predict the dependent variable. If we cannot reject the null hypothesis, then that independent variable is not significant, okay, and probably should not be included in the particular model. Okay, let's look at an example, okay, on the colleges and universities data. Okay, and we are using this data to predict student graduation rates using several indicators. Okay, we have here median set, okay, SAT value, acceptance rate, expenditures per student, top 10%, okay, from the high school results, and graduation percentage. So the graduation percentage, okay, we can see that the model for graduation percentage is equals to 17.92 plus 0.072 SAT minus 24.859 acceptance minus 0.000136 of expenditures minus 0.163 top 10% in high school. The signs of some coefficients make sense. Okay, Higher SAT scores and lower acceptance rates suggest higher graduation rates. Okay, however, we might expect that larger student expenditure and a higher percentage of top high school students would also positively influence graduation rates. Perhaps the problem occurred because some of the best students are more demanding and change schools if their needs are not being met. Some entrepreneurial students might pursue other interests before graduation, or could potentially be a sampling error. The value of R-squared indicates that 53% of the variation in the dependent variable is explained by these independent variables. Okay, and if we look at the coefficients, okay, we can see that all coefficients are statistically significant.